started so you can have time, okay?
Sure, whenever you want.
Okay.
Like I said, it's going to be pretty short. Man, I think.
Well, Cyrus might. First of all, I want to welcome all of you who are in the room here tonight, together with all the people that are online right now. So thank you very much for coming to this event. And the history of this event has taken a few turns along the way. It was originally titled Back to Our Roots. And the reason for that was my own personal experience of going to the University of Scranton and then hearing about Maryknoll at the University of Scranton. And in 1913, Maryknoll, James Father Walsh, with the first seminarian, went and opened a house on Clay Avenue, 640 Clay Avenue. And from that house, they studied at St. Thomas College, which became the University of Scranton. So that from the very beginnings of Maryknoll, the University of Scranton has been instrumental in kind of our education and the desire that they had for an apostolic college. They even called the house at 640 Clay the Baynard, and eventually it was built out in Clark Summit. When I first went to the university in Scranton, I actually lived at 520 Clay Avenue, 1 block away from where the house was. And Cyrus, who was with us also, was living in that building with me at different times. So for me, that was kind of the reason. Do people really understand the University of Scranton's role in terms of the beginnings of Maryknoll? But then in conversations with among ourselves, another title emerged, something like Friends in Conversation. Friends talking about ourselves. And the highlights of these 4 friends have been a significant kind of support group for myself, to the point that I kind of labeled this community myself, Church on the Porch. And it was Church on the Porch, which was every couple of weeks, Declan would invite us to his porch, which was a very nice porch screened in, for conversations and drinks. So, but then it turned out that as we looked for we looked for a title for the event, we eventually settled on this title, Beyond the God We Think We Know. And I think it's a title that captures our communal struggles to talk about the one in whom we believe or do not believe. Each one of these friends of mine brings a richness into those reflections, and while they have always desired to come to Maryknoll for a retreat, when we finally agreed that they would come to do a retreat here, I asked if they would graciously offer some kind of input, not only for ourselves on retreat, but for the community here. And so they graciously agreed to that, and certainly it has grown much larger than we thought it was going to be originally. And with live streaming and the number of people who are participating in this, what we really would like to do is invite you onto the porch. Come into the conversations, listen to the conversations of us, and we listen to your conversations, and feel free to question and to contribute to any of the presentations that you might hear. One of the person that's here is Cyrus Olson, who's in the back. And Cyrus is going to respond to each one of the presenters, and then he will kind of facilitate anybody who wants to raise a question or make a remark about them. Cyrus is a nimble, this is what I wrote. Cyrus is a nimble and brilliant thinker who moves easily from talking about Wittgenstein and process theology to diviner wisdom in Uganda. from Bauman's fluid modernity to the ethics of emerging technologies at the Oxford Collaboration on Theology and Artificial Intelligence. Cy was on my interviewing committee, and he asked me, since he hadn't heard of Maryknoll, what is the difference between Maryknoll and the Jesuits? And I won't say what I said, but his answer to me was, that's a bit cheeky. And I thought, all right, that's not in my active vocabulary, but okay, I'll take it. So he will be responding to each one of the people that are here, and the presentation tonight is by Declan Mulhall. Declan is professor of physics in the physics department, quantum mechanics, and other kinds of stuff that he teaches. But on the porch, Declan has been a source of challenging all of us to live what we claim to believe. He has been in the forefront himself of defending the rights of immigrants and the Palestinians of Gaza. He has been in the forefront defending and advocating, legally advocating for foster children through the CASA program. And he has participated actively in the University of Scranton's campus at the Dallas Correctional Facility. And one of the biggest things that he has offered in those conversations is to protect the dignity of those students and to look upon them as students and not to investigate why they're there, and to treat them as we would treat any of the students on campus. So with those words, I open it up to Declan. Welcome, and thank you very much.
Thanks very much. Can you all hear me okay? Okay. And so I won't ask you if you can all understand me okay, because I don't want to know the answer. So thanks, John, for that nice introduction. My plan was to give you a very simple and convincing, basic description of the origin and fate of the universe, as we're pretty certain that we know what it is. And when I say pretty certain, I mean, like, you really don't want to bring a knife to a gunfight. We're pretty certain, okay? When I say we, I mean the physics community. So this is a talk about physics and the physical world and how we interrogate the physical world and all the rest of it. This isn't a talk about meaning or how we construct meaning or how we live in a world with injustice and stuff like that. This is a talk about how we understand the physical world. And I should probably say historically, the reason I'm here is because most of my best friends are theologians, and I don't know how that happened, but here we are. I must have been a bad dog in a previous life, and the Hindus are right. And I talk to my friends, and they go on about, like, they'll say things about God. And every time I press them, I don't know what they're talking about. They will not say what that word means. And they'll talk for 10 minutes and not repeat themselves, and the question won't be answered, and I won't be any the wiser. But I will feel that I'm somehow wrong about something, and they have this kind of a smug look of the people who are correct about something. So I'm going to short circuit all that now, and I'm going to give you a very simple story about what is actually it really is a simple picture about the physical world. My name is Declan Mulhall. I'm from the University of Scranton, and I was trained up in physics in Michigan State University. I got a PhD there under the guidance of Vladimir Zelevinsky in the National Superconducting Cyclotron Lab. So my chosen specialized field was theoretical nuclear physics, and I won't apologize for that. So I'm going to make some comments about the size of the universe, and I'm going to make comments about the universe versus the observable universe, because unlike my theologian friends, I'm not afraid to tell you what I mean when I use a word like universe. And I'm going to explain to you, I'm going to make some statements about the universe. I make the claim that the universe is expanding. And then I'm going to back up that claim and tell you, this is how we know the universe is expanding. Then I'm going to describe two theories that were two theories that were attempting to explain how the universe could be expanding. And then this all came about, I think, in the 1930s. Then in the 20s, we figured out the universe was expanding, and then some theories came about in the mid-20s to 30s. And then there was a moment in the 60s where one of those theories was killed and the other was proven to be the correct theory. That's called the Big Bang theory. And I'm going to tell you the evidence for the Big Bang, and then we're kind of done. Once I describe to you the evidence for the Big Bang, and once I tell you what the Big Bang implies about the past and the future, then it'll just be like, well, what are the implications? And then I'll say some things that may or may not be disturbing to you. You guys probably won't be disturbed at all, but I find it somewhat disturbing. Okay, well, yeah, I'm going to tell you about the past and the future. The first thing I'll say is that the universe is very big. We'll start with the solar system. The solar system is very big. There's a common pedagogical model called the grapefruit model, where the sun is like a grapefruit. If you imagine the sun as a grapefruit, then the earth is the size of the tip, the ball in a ballpoint pen. And it's 10 yards away. So I know what 10 yards is. Probably like, you know, from here to the window. Imagine the corundium tip, the ball in a ballpoint pen, and a grapefruit over by the window. That's the solar system. It's really big. Now, if the sun was the size of a grapefruit, and it was in Los Angeles, our nearest star would be in New York. So the Milky Way is very big. The Milky Way is so big it takes light 100,000 years to go across it. It's pretty big. And our nearest star is on this scale, is the width of a continent. So imagine a grapefruit in New York, a grapefruit in San Francisco. The point is that the solar system is big. The universe itself is very, very big. I'm showing you a picture of what the so-called Hubble ultra-deep field. Now, what you're looking at is this. You're looking at an area of the sky that's the equivalent of 1 square millimeter, or a grain of rice, held at arm's length. And how much of the sky is blocked off? So what the people in NASA did, what the astronomy community did, was they said, let's look at the darkest, most uninteresting place in the sky where nothing is happening. And we're going to point the Hubble Space Telescope ahead and leave the shutter open for 10 days. Now, that's not the way it works. What you have to do is you have to take photographs because it's an orbit. It's a satellite that's going really fast. But there's ways, that's just a technological detail. What it amounts to is pointing the telescope at this incredibly small, dark part of the sky where there's really nothing happening, leaving the shutter open and seeing, well, is there anything really there? And this is what's really there. This is an absolutely unbelievable picture. This is the Hubble Ultra Deep Field. It's smaller than a 1 millimeter square piece of paper held 1 millimeter away. And it is teeming with galaxies. Those points aren't stars. You couldn't see a star. The things that are up close are stars. But most of that stuff is galaxies. Now I'm going to show you. I'm going to show you how small this is in the context of the full night sky. We do it like this. We go here, and then we go here, and then we go here. That's the Hubble Ultra Field. And we're pulling back. We're zooming back. This is a tiny part of the sky. And that's a grain of rice, smaller than a grain of rice held at arm's length. And we're pulling back, and we're still pulling back. Now we're up to something like an erasure tip held at arm's length. And we're still pulling back. We're nowhere near. Sit down. Don't go anywhere. We're only getting going. Now look, it's gone. And it really was a boring part of the sky. There was nothing in it. And soon we'll see what we can see the night sky. And it was in there. That's what we just saw. That's where, hold on, that's where F5. That's where that was. So my point in all this is that the universe is really big. I'll tell you how big it is right now. Spoiler alert. it's 92,000 million light years across. So when you look over in that direction as far as you can see, then you look over in that direction as far as you can see. The distance between those two things would take light 92,000 million years to get there. And of course, we know that the universe is 13.72 billion years old. So you're thinking, well, 13.72 billion years this way and 13.72 billion years that way. That should just amount to around 27 billion years. But the universe is expanding, so you get caught out. It doesn't really work that way. It really is 92,000 million years wide. So now I'm going to define my terms, and theologians take note, have a bit of manners, and maybe you could start doing this yourselves. The observable universe is all the stuff that we can see, all the stuff that we can observe. That's not all the stuff that exists. All the stuff that exists is different. Now I'm going to stand over there, and I'm going to ask you to imagine a sphere centered around me. Here I am. This is a sphere centered around me. Supposing that was the observable universe. In other words, from the earliest time, the farthest back I can go, I can only see what's at the center of the sphere. Well, somebody over here, they can see a little bit more stuff to the right and a little less to the left. They see a different universe. So the actual universe that exists may be infinite. We don't know. Physicists think it's infinite. We have very good reason to believe it's infinite. But we can't really prove it. We're fairly sure it's infinite. So, but the observable universe is a small part of that universe. And this will be really important to remember, because when we talk about the Big Bang later, I'm going to show you part of a very small video by the guys at Minute Physics. Minute Physics is a YouTube channel run by an artist and physicist, and it's really good at explaining stuff. And it'll walk you through what I just said. That the Big Bang is a horrible name. There wasn't a point in space. There was just infinite space that was scaled differently. Imagine a rubber sheet being stretched. We'll get to that though, so don't worry. So all that is visible to us is the observable universe. It's 92 million light years across. Telescopes look into the past because light takes time to travel. So when I see something, a distant galaxy, I'm seeing it as it was, not as it is. We don't know how things are. We see them as they were. That's just because the light has a finite speed. This isn't deep. This is just like logical, and when you get into the details, this is where you find yourself. Someone at the edge of our observable universe is at the center of a different sphere, so they see a different universe. But they could possibly have the same conversation. The universe is probably at least, I'm going to say a number you probably won't even understand because it's so ridiculous. 3 by 10 to the power 23 times bigger than this. That means what's 3 by 10 to the power 23? Imagine you have a liter of gas. I don't know, imagine you have it would be comparable to the number of atoms in this room. That's 3 by 10 to the power 23. Well, the universe is probably 3 to the power 23 times bigger than the observable universe, meaning that all that we can observe is equivalent to, on the lower end, equivalent to 1 atom in all the atoms in this room. And so we might as well say that's infinite. Sure, it'll do until infinity gets here, even if the universe is bounded. What do we mean by the universe is expanding? Now, I'm going to tell you that the universe is expanding. That means is this, that the galaxies farther away from us are receding. So, here I stand, and I look out in the whole world, and I can see stuff off that direction and off that direction. The stuff that's far away is receding from me, and the stuff that's farther away is receding faster. That's bizarre, but this is where we are. Of course, there's loads of images. Imagine, here we go. Imagine you're a spot on a balloon. That spot on the balloon, as the balloon inflates, all the other spots get farther away. And the ones that are farther from the original spot get farther away faster. This isn't deep. This is what it means to say the universe is expanding. But the really common image is raisins in a cake. And as the cake is baking and rising, all the raisins get farther away from each other. And suppose you pick a random raisin, well, this guy is moving away from me as the cake rises. But the guy that's farther away is moving away faster. We actually have an intuition for this. It's not that deep. So when the universe is expanding, what we really mean is the stuff that's farther away is receding faster. So how do we know? Now, this is important, and it's very simple. How do we know the universe is expanding? Okay, listen carefully, what I'm going to tell you. When you're standing on the street and you see an ambulance going by, or even a fast car, you're in New Jersey, some punk with a rice rocket zips by. You hear a high pitch and then a low pitch. Like the Formula cars, right? That effect of a change in pitch, a high pitch when something's coming to you, a low pitch when something's going away from you, that's called the Doppler effect. That works for sound, it also works for light. Look at this little cartoon here. There's a green car, right? Now hold on. Okay, there he is. He blows the horn. Look at the sound waves. Now as he takes off, the sound waves in front of him are closer together. They have a short wavelength. The sound waves behind him are farther away. They have a longer wavelength or a lower frequency. So the sound waves in front of him are bunched up. They're a high pitch. The ones far away are a lower pitch. So all you have to do is this. If you know the frequency or wavelength of a signal coming from an object, if you know what it is, if it's not moving, and then if you see how it changes, you can tell, is it moving to you, is it moving away from you, and how fast it's moving to you, using the Doppler effect, or how fast it's moving away from you. There's a parameter called Z that astrophysicists use, and that's the change in wavelength divided by the wavelength. And you don't have to worry about that. Now, I'm going to just put it up there because people are taking more seriously if you slap up an equation. But that's a mistake, actually. Okay, so I've explained to you the Doppler effect. What's that got to do with a star? Well, look at this. You can see high-pressure sodium street lamps. Those orange glow street lamps, right? The way they're made is this. They have sodium gas in them, and it's heated up, and you run an electrode through it. And what you're doing is you're running a current through some sodium gas. When you run a current through sodium gas, sodium is an element, it's a metal, but you can actually make a gas out of anything. So you can run an electric current through this sodium gas, and it excites the sodium atoms, and then when the sodium atoms de-excite, they give off some light. Looky here. Look where the pointer is. This is the sodium spectrum. That is a very bright orange line. And then you've got some red, you've got some green, and you've got some blue. That's the colors that come off the sodium lamp. This is called the spectrum of sodium. If you see these colors, you know you've got sodium. It will be a hell of a coincidence for these exact colors to come up somewhere else. If you see those colors, you got sodium. Okay, so here's the deal. Imagine these lines here, the black lines represent the lines of some gas at rest. If you saw all those shifted in a way that exactly matches the Doppler shift, you'd know that this was a source with this spectrum moving away from you. That's what you'd know. So this guy with a pipe in his gob, his name is Hubble, and he's particularly pleased looking because he figured out the following thing. He figured out that stars and galaxies that have sodium in them, they all do actually, that the sodium lines from distant galaxies are shifted in a way that says that they're moving farther. So he could tell you, he could look at some light, and he can tell you how fast that source is moving. And he knew how far away they were. And he saw that the farther away ones were moving faster. This is an example of the data you see. So here's a cluster. Here's a source in the Virgo cluster. It's 78 million light years away, so it's still in the Milky Way. And you see that, I know it's very faint here, you see that little dark line there right above the pointer of my mouse? That's the sodium lines. And he can tell how fast the thing is moving. It's moving at 1,200 kilometers every second. But look, where's my mouse gone? Look at this lad. This time it's over here. That's shifted more to the red. It's receding even faster. This one is going 15,000 kilometers away. Look at this lad. Those sodium D lines, they're down here. And in this case, they're down here. and in this case, they're down here. Look at this. These are going shocking fast. These are going 61,000 kilometers per second away. That's a source in Hydra, and that one is 4 billion light years away. Yeah. Okay, so this is actual data, and this is what they do. Now, you'll be delighted to know, if you don't believe me. So I didn't put in current stuff because you can get really swamped with the technology. But there's lots of new automated telescopes. There's a telescope called DESI, and what it does is this. It's really cool. It's got a whole bunch of optic fibers, and it's got little robots. And every night it looks at the galaxies, and it picks out a star and shines the light from one star onto one optic fiber, and another star onto another optic fiber. And every night it takes thousands of readings from stars, and it analyzes their motion. It's absolutely fantastic. This is old school stuff, where you do it one photograph at a time. Now they've got robots doing it with telescopes. Okay, now you're sitting there and you're thinking, this guy's worse than a theologian. He's just saying things and sure he's not backing it up. He's just saying that faraway objects are receding faster. Now you're sitting there saying he has definitely convinced us that he can look at a light source and see how fast it's moving by looking at the shift in its color. But he doesn't know how far away they are. So that's a big question. How far away is a star? Or how far away is a galaxy? Yeah, so what you need is this. You need a thing called a standard candle. I want you all to imagine a landscape. So if you look out onto the valley, and you give a couple of thousand volunteers, you give each of them a 100-watt bulb, and say, hold up this 100-watt bulb. Then you can see how far away that person is by looking at the energy from their bulb. The far away ones are dimmer. The closer ones are brighter. So you're done. If we've all agreed we have a standard candle, a standard 100-watt bulb, we scatter them about the landscape, then we can do mapping. We can say, oh, you're over there, you're over there. I know how far away you are because of how dim you are. Because remember, all this data is taken by scientific equipment that's calibrated. And it gives you a number. And that number translates into, in this case, a distance. So we need a standard candle for a thing like a galaxy. Well, what would that look like? But you don't know, you see a bright star. You don't know, is it a dim star that's close? Or is it an incredibly bright star that's far away? Most stars are useless for this purpose. It doesn't work. There are some standard candles. This is really important. This is what brought the whole thing. This is super important. I can't stress it enough. And your woman there, Henrietta Leavitt Swan, she studied thousands of variable stars. There were things called variable stars. And this is so fortunate. Fortunate? Is there something else going on? No, it's just fortunate. You can explain this physically. There are stars, and they get brighter and dimmer and brighter and dimmer. And their period, the time between brightnesses, is proportional to their luminosity or their wattage. And so you're set. Now we've got stars, and we know what they are, and we can look at them. And we can know the wattage of their light bulb by measuring the period of oscillation of their brightness. Now we know how much energy they're putting out. Then we know how much energy we receive with our telescope, so we know how far away they are. That is the trick. Now look at this. This is an animation of a so-called Cepheid variable star. I just described a Cepheid variable star. Look at it. It's bright. It's dim. Bright. Dim. Bright. Dim. So look at this, night after night. And here's one example of it. And this is a Cepheid variable with a 9-day period. Between here and here, some hapless grad student took this data, and they see that every 9 days, it goes from bright to dim to bright to dim. And because they know that the period is 9 days, they can consult this graph, and they know how bright it is. And so now we know how bright something is. And then we can see how much energy we're getting. It's apparent brightness from this distance, and we know how far away it is. These are called variable Cepheids. This is the Milky Way. There's us. Obviously, it's not us, because you can't get that far away and take a photograph. But, okay. But this is the center of our galaxy, and those red dots are variable Cepheids. So they happen. They happen with enough frequency that you can look at a galaxy, well, you can certainly look at a Milky Way, and you can look at a nearby galaxy and see them. That's called a standard candle. So now we can make that following claim. we can say, we can know the distance, and we can know how fast something is receding, and we see it lies on a line. And the farther away the thing is, the faster it's receding. That is why we know the universe is expanding. Now you're sitting there thinking there is no way you can go outside of our galaxy or local galaxy cluster and see this. There are other standard candles. And I'm going to tell you about, yeah, I have time. I'm going to tell you about another standard candle, a particularly interesting one. There's a lad called a Type 1a supernovae. Listen carefully. A Type 1a supernovae. This is what this is. You have a neutron star. You have a white dwarf star. That's the type of star. And he has a colleague. And they're circling each other. Mr. White Dwarf Star is stealing. He's stealing matter gravitationally from his colleague. Because some stars are very big and have a very large gas cloud around them. And you have an accretion disk. So this white dwarf star is gravitationally vacuuming material off this star. And it's getting bigger, bigger, bigger. But there's a theory, it's a well-known theory, and it's well justified, that when these white dwarfs get to a certain mass, bam, they go supernovae. And it's one mass, and all these explosions are the same. So what you do is this. You look at a galaxy, and you wait. Every night, in every galaxy, there's a couple of these. No, that's not true. That is totally, sorry. That is not true. I should not have said that. I should have said that every night, when we look at our night sky, you'll see a couple of these. Like, occasionally you'll see a Type 1a supernovae. And when you see one, you know how far away that galaxy is. That is a standard candle. Very interesting, actually. It's a very beautiful thing that happens. I could tell you a very beautiful thing about how these Cepheid variables work, but there's no point. If we have time later on, and you're interested, I can tell you. It's very simple. Okay. So this is Hubble's law. Hubble's law tells me that if I go on the horizontal lefty-righty axis is distance in billions of light years, and the uppy-downy axis is the velocity with which they're receding, and the lads that are farther away have a bigger velocity, and it's a straight line. There, the universe is expanding. Okay, so what does that mean? Well, that means we have a... Okay, hold on a second. Okay. Okay, I'm going to show you one of these universe is very big photographs. So look at this. This time we're looking at the extreme deep field because everybody was so happy with the deep field, the ultra deep field. I'm going to show you how big the universe is again with the extreme deep field. Would you look at that little square? The moon is beside it just to show you some perspective. But it's taken at some location in the sky, once again, where there is nothing happening. I mean, it's a completely dark part. You could have went there. Probably if the resolution was better, they'd say, no, this is better. There's nothing happening there. And after 23 days of exposure time, collected over 10 years, this is what they saw. And what you're looking at is some of the oldest objects in the universe. The red lads. These are red not because they're red. I mean, what the hell does that even mean? Because of red paint? I don't know. No, these are red because they're so far away, they're receding so fast that when you're going away, blue light turns to red. These are red-shifted. Yeah. And so I told you that red-shifted things are farther away. So this is what we can do. We can line up these things with the age of the light. So you can go to this photograph and you can pick out all the stuff and say, this is all the stuff that's less than 5 billion years. This is 5 to 9 billion years. And this is more than 9 billion years old, getting back to the early universe. So this is what you can do with these things. I want to make an important point because it's very confusing to people when they say the universe is expanding. I mean, is that why I'm getting fat? No, I'm getting fat because I'm a weak individual. The universe is expanding. So I guess the question is this. What expands in an expanding universe? It's a very good question, isn't it? Because you think, well, Jesus, I mean, if everything expands, then we're all just a little bit bigger. And how would you notice, you know? It would be like looking at a photograph and you just walk up a bit closer. I mean, nothing's really changed. No. The thing that expands in an expanding universe is the spaces between bound objects. Galaxies are bound together with gravity. That's a force. That force easily overcomes the expansion. So galaxies get farther away from their neighbors if they're not gravitationally bound. But galaxies themselves don't grow. We don't get bigger in an expanding universe. Hydrogen gas doesn't get bigger. But the distance between one galaxy and its distant neighbor, that gets bigger. And actually, we don't really talk about galaxies. We talk about galaxy clusters. There are clusters of galaxies, and they're receding shocking fast away from each other. So think about it, when you're baking the cake, the raisins don't get bigger, they just get farther apart. I don't know if that's deep, it's probably not deep. Okay, so now we have a problem, so we have to explain all this. So we have an expanding universe, so we need a theory. So George Lemaitre was a priest and a good, by all accounts, a good physicist and mathematician. And he said, well, sure, it's completely obvious. Sure, if the universe is expanding, if you run the video backwards, sure, it was all coming from some primordial atom. So George Lemaitre said, sure, there was a primordial atom, and that was the start of everything. And sure, wasn't that God creating stuff? But he didn't define God because he was a theologian. And theologians, I'm sorry, theologians do not define God. I mean, they think they do, but they don't. Okay. But other people said, no, that's ludicrous, because they're right. A Big Bang, it does seem ludicrous. I mean, if you never heard about this, so it's part of our cultural, there's memes about it. If you never heard of a Big Bang, sure, you'd have someone institutionalized. You'd be worried about them if they started talking like this, that the universe came from a tiny little atom. This is nonsense. So a more sensible theory is the steady state theory that sensible people subscribe to. And the steady state theory is this, that yes, the universe is getting bigger because there's a force that makes it get bigger, and the universe doesn't change over time because its density is maintained at a constant level by the generation of matter. New matter is generated. There, problem solved. It's getting bigger, but also new hydrogen. And how much new matter, if you go through the numbers, the amount of matter you have to generate is 1 hydrogen atom per cubic meter every billion years. I mean, that's a small ask. So all you're left with to do now is if you can find some theory that'll explain the 1 hydrogen atom per cubic meter every billion years, then your sensible, steady state picture of the universe, which is intuitive, that wins. And this Big Bang nonsense is sent to the trash heap of failed physics theories. But the problem is this, that the Big Bang theory requires, it tells a story, and the story can be checked. So this theory needs to explain the redshift of distant light, the cosmic microwave background, which we'll get to in a minute, and the creation of new matter. So if you could, so that's what the steady state suggests it's the creation of new matter. Well, you better explain it. So some ideas of the steady state model include there's tired light. This guy called Zwicky, who was a fantastic physicist, and he really did an awful lot of stuff, but he's not very well known. He said, look, here's what's going on. The reason that the distant galaxies are redshifted is because light kind of runs out of steam after a while. It gets tired. Right, which is ludicrous, but here we are. And then Einstein said, no, there's a cosmological constant. There is a force in the world that makes things expand. So, okay, that's, Deus ex machina, I guess. So here's the end of the story. The Big Bang theory demands a timeline. It demands that the history of the universe has a certain shape. And there's lots of opportunity for data to kill or support a theory. And so I'm just going to give you some of the moments that the Big Bang demands happen. That at very early on, and when I say early, to ludicrous times, like 10 to the power of minus 23 seconds, the universe consisted of a hot electron quark soup. Then at one millisecond, protons and neutrons were made. And then after about 330,000 years, so there was protons and neutrons and electrons and light floating around. Then after 330,000 years, hydrogen gas was made. Once that happened, the universe went transparent. And when the universe went transparent, all that light just kept going on, not being scattered. It was no longer scattered anymore. It was no longer bouncing off things. It just went free. And so, as the universe expanded, that light was off doing its thing, just going out. So ever since then, that light has been expanding with the universe and getting shorter in wavelength and lower in temperature, and it has turned into the cosmic microwave background. So there. That is what the Big Bang Theory does. So there better be a cosmic microwave background, and there better be 4 times more hydrogen than helium. And lo and behold, there is a cosmic microwave background. And there is 4 times more helium than hydrogen. I think I'm getting, or it could be, I've got those elements bounced back, but I'm not too sure. So this completely vindicates the Big Bang theory. I mean, there is no other theory that will give these results. The cosmic wave background is exactly as predicted to this level. I'm going to show you, this blue line is what theory expects. The black dots are data from the cosmic microwave background. There's error bars. There's like little lines. They're so small, and this blue line so perfectly, you can't. They're 1/40th the size of the dots. Completely. So there was a line was made. This is the unit. It started to tick incredibly 10 to 23 seconds, and an electron, and it just expanded there because we'll be here all night. Here's the a bit, but then was the parent, and then there was a couple of bit years, then stars formed. Is formed. And well, what about the future? So the future is Andromeda galaxy is 2.5 million light years away. This is here, and it's coming at us. It's in this is our galaxy. In about 4 to 8 billion. When we look in the night sky, or that's something to look forward to. That's something to look forward to in 4 billion years. And far the sun will turn into a red in about 5 billion years, and his we're screwed. So all over in billion years. The universe is such that everything in our local cluster of galaxies will turn anything outside of it in about 2 million years or 2,000 billion years. There is fast that light it goes from blue to infrared waves to in 2 trillion years when astronomers look out in the night sky, they're going to see a static galaxy. They won't see microwave background. They won't see distant galaxies. They'll see a universe with its own galaxy sitting in infinite darkness. There. So conclusions. The universe is big. The universe is expanding. This expansion is accelerating. So all galaxies will be away from so fast they will be invisible. The cosmic microwave background will be invisible. Our galaxy will be floating alone in a vast dark cold space. Stars will stop forming in 100 trillion years. So things are bad enough, but in 100,000 years, stars will stop forming, and then 10 trillion years later, the last formed stars will give out, and then we'll be properly screwed. There'll be nothing. They'll just be like the cold embers of the stars in our local galaxy. So repent your ways. Okay. Good news is that in 5,000 million years, the sun will expand into a red giant and swallow us up and spare us. Okay, that's it.